My name is Prateek Jaipuria. I am from the USC Information Sciences Institute. I'm a computer scientist there working for the last 2.5 years. I'm a part of the DITTER project, which operates DITTER Lab, which is an advanced testbed facility to conduct critical cybersecurity experimentation. Before joining ISI, while doing my master's at Duke University, I was involved with the Genie project there. And so Genie is again a federation of a few of the most widely used network testbeds. So in all, I've worked with network testbeds for about 5 years now. And I'm here to talk about our team's work on a calibration methodology for network cybersecurity testbed environments. This piece of work that we wrote and submitted as a work in progress to Razor was led by Vineet Kadke, who was a student researcher at ISI. Unfortunately, he could not be here to present this work. This work is done under the supervision of Alifia Hussain, who is also a computer scientist at ISI, has been working there since 2011, and she leads the experimentation lifecycle tools development effort as part of the DITTER project. Okay, so let me begin by defining what we mean by calibration here. So calibration for us is to adjust experimental results to account for testbed inefficiencies, external factors that are not under the control of an experimenter, in order to allow correct interpretation of these experimental results, to be able to correctly compare results obtained from distinct runs of the same experiment. And what we are implying here is that experimental results can get skewed, distorted because of some of the inefficiencies in the test bed, and we need to calibrate the results to remove the noise, the error. Right. So what I'm trying to show here with these two figures is, if you look at the first figure, it's just some sample raw data, and what we are seeing is data from 3 repeated runs of the same experiment setup, same experiment procedure, and what ideally we would expect is to see the same result coming up. But that's not so, and what we think is it can be because of the inefficiencies of the testbed. So before reading into the data, before analyzing that, we should calibrate the results and then try to understand that. Now, calibration is a hard problem to solve. And before actually trying to find the solution for the problem, we need to be convinced about the need for calibration. And during this talk, I'll try to put up a case for the need for a calibration methodology. So the way I've structured this talk is I'll talk about 2 case studies, 2 projects that our team was a part of, that convinced us about the need for a calibration methodology. And by the end of this talk, I hope to convince you all too. The reason I chose to talk about these 2 case studies is I wanted to take the audience through the same experience, same journey we went through, so that it help us as a group to relate to the problems that we get. And so these 2 case studies actually refer to 2 different sources of error. The first one focuses on the problem related to system specification and paying attention to details while describing an experiment topology, experiment setup. And this is not the exact problem we are trying to address with calibration, but it's an intermediate problem of some sorts. And I think talking about it will help us appreciate this other problem of analyzing the experiment results correctly. So this work came about while I was working on this other project, the cyber physical systems experiment, where we were specifically trying to see the behavior of a defense against a denial of service attack. And as the first step, we were trying to emulate an attack scenario. So as you can see in the picture there, we had divided the entire west coast of the United States into 4 different regions. We were trying to attack each region at a time. And on this project, we were working with collaborating with a couple of power engineers also. So we came up with a test scenario, we implemented it, tested it, and it was all working fine. So we went home this day, we came back the next day, and our testbed resources had been taken away. So what we did was reinstantiated our experiment. Was the same experiment, reran the same experiment procedure, but we were not able to see the same results. We were not able to replicate the attack scenario, and we did not know why that was happening. So first thing we thought was because we were working with these different other power systems, PMUs, RTDMS, probably some of these systems weren't working correctly, or the interconnection between these systems had gone wrong somewhere. So we had to spend a significant amount of time and effort looking into all of this. But once we were convinced that other systems were just fine and it had to do something with our own testbed resources, we looked deeper, and what we found out was both on the attacker node and the node being attacked, we saw a huge amount of packet losses. Now, we did not know why that was happening. We did not have an clear answer for that, why the sudden packet loss. And the first question that popped up in our mind was, did any part of our experiment change between the two runs? So to answer that, let's talk about the current state of the test of some of the most widely used network testbeds within the research community, and these are some of the testbeds that we consider within our work. What these testbeds do today is provide the experimenter with a set of tools that encourages the experiment to describe their experiment topology at a very high abstract level, where you represent different parts of your topology using nodes, and then the focus is on interconnections. How do you interconnect these nodes? And this experiment abstraction has been very successful. It has its own advantages. Right? The rapid instantiation is one of those. So you can access the web user interface of these testbeds, where you can just drag, drop nodes, connect them using links, and there you have it. Your topology is ready to be instantiated. The other thing you can do is write a topology description. And if you do it at a very high abstract level, it's usually easier to do, quicker to do. The other advantage with that is portability. So the last I checked, there were about 25 to 30 instances of Emulab-based testbeds in production, and all of them support the NS2-based topology description language. And this is a snippet of that for a very simple topology, two-node topology. And so until and unless you go into the testbed specific details, this description is portable. So you can take it to any of the Emulab-based testbeds and you'll be able to instantiate an experiment. And what you will get is the resources that are allocated to your experiment will have the same abstract view to nodes connected by link. And this is what hurts us experimenters. What we don't see is underneath this abstract description. We do not pay attention to the details of the underlying resources. Resources allocated as part of different instantiations of the same experiment topology can have different characteristics. And that's because all the facilities that I talked about are shared facilities. So suppose whatever resources were allocated to one instantiation of your experiment might not be available the next time you try to instantiate the same experiment. Or the allocation algorithm might just give you some other resources. The other thing is we've been working with virtualization a lot these days. We want to do large-scale experiments, 10,000, 100,000 nodes experiments. We don't have so many physical resources. So we have developed these virtualization capabilities, which offer differing degrees of fidelity in individual elements. So we can do virtualization using VMs, thread-based virtualization, and other such things. We also work with federated testbeds. So there are resources that are only available at specific testbeds, and we want to combine those as part of one experiment, and there we use federated experiments. So because of all of these and other such factors, and the fact that the experimenters provide an abstract description of their experiment topology, what happens is different instantiations for the same experiment end up having different characteristics at a very high level. These could be physical resources, virtual resources, resources on different testbeds, right? So for an experimenter who comes to a testbed to do an experiment, the first thing he or she needs to do is to create a valid representative environment of the system under test on the testbed. Right? You need to be able to define the system constraints, the low-level characteristics of the system that you require. And as we saw, that the abstract description that we use today hides away a lot of these essential details. And so until and unless the user has specified the low-level system constraints as part of the topology description, there's no guarantee that the allocated resources will end up emulating the system under test correctly. And that is what made us think, if it was some resource inefficiency that was the cause of this high packet loss, right? And to investigate that, we set up a very simple topology on DataLab, 2 nodes connected by a 1 gigabit per second link. And then what we did was we flooded packets from the sender to the receiver just to fill up the entire link. And this was an attempt to recreate this packet loss scenario that we were seeing. And we were easily able to replicate it. And we did not have an answer to why that was happening, so we did a couple of different experiments. And one of the experiments that we did was to understand, to relate the packet size that we're using in our attacks to the loss percentage. And what we should focus here is on the behavior, the trend of these graphs. But what we see is with small packets, we saw a high amount of losses. As we increased the packet sizes, there was a reduction in loss. And at about 250 to 300 byte-sized packets, the loss went down to 0 and then remained there. And again, we did not have a clear answer for this, right? So we did, again, spend significant amount of time, effort, looking into all of this. Finally figured out that it was because of some hardware inefficiency. The network interface card on the hardware that we were using, it was a 1 gigabit interface, and according to Intel specifications, it could process about 500,000 packets per second. And doing simple maths, we came up to this result that to fill up a 1 gigabit link with 500,000 packets per second, we needed packets of about 268 bytes per packet. Smaller packets would mean more number of packets to fill up the link, and hence the loss, because the link could not process those many packets. And bigger packets would mean less number of packets and hence no loss. So we figured out that it might be because of this inefficiency, but this experiment was working one day and then stopped working the other day, right? So something might have changed or should have changed between these two runs. And when we thought about it, these were 2 different instantiations of the same experiment, right? So we could have got different resources. So what we did was run this particular experiment on diverse hardware available as part of DataLab. And this figure has a lot of numbers, and I don't want you to just try and figure out these numbers. But what the high-level message here is that there was variability with diverse hardware. Different hardware behaved differently, right? And each of these hardware had a different loss behavior, and it might have been because of each of the hardware having a different network interface card. Might have been because of some other characteristic. We have not understood that. But what I want you to focus on is this particular row with 100 bytes per packet. This is what we used to do the cyber physical system experiment emulating the attack scenario. And as we see, some of the machines available at DataLab show 0% loss at 100 bytes per packet, and some of them show a huge amount of losses. And this is probably what hurt us. We got one machine one day and some other machine the other day. So now that we understand that the problem was not defining the experiment environment correctly, not paying attention to details, does that solve our problem of correctly emulating the system under test? Can it be guaranteed that tested resources with the default configuration will be able to fulfill the required system constraints for any and every experiment? And the answer is no there. And for that, we should just try to look at another row within the same data. If our experiment we wanted it to work with 50 bytes per packet and wanted a 0% loss, there isn't any hardware available in DataLab which would have provided us those system constraints, at least with the default configurations, right? So how do we solve this problem? The solution that we came up with was tuning. So what we thought was, why not tune the systems that are available? So the only constraint for this particular example was that we wanted 0 packet loss. right? So what we did was we tried with a simple tuning mechanism. What we did was we just increased the buffer sizes both at the software and the hardware level to tune the system to make it abide by the required system constraints. And what we observed was yeah, we were able to bring down the losses to zero, and it worked. So we had the same question again. Does correctly representing your system and then tuning, having a tuning solution solve the problem of correctly emulating the system on the test? Can tuning be a viable solution in all circumstances? And again, the answer was no there too, because there are cases where your available resources, even after tuning, there may be cases where they are not just capable of meeting the required system constraints, right? Or there might be some other test bed specific properties that just cannot be adjusted, cannot be tuned, right? In this particular case, we just had one constraint. We could have experiments where there are a set of characteristics that you want, and there is not a tuning mechanism to tune all of these different constraints together. And in such situations, tuning is not a viable solution, right? So to look into this further, what we did was we just tried to study some other characteristics with the same setup. What we saw was one of the characteristics that we thought intuitively would be adversely affected by the way we tuned the system was delay, because we had bigger buffer sizes to reduce the loss. Now packets could stay there in the buffer for much longer rather than being dropped. So we studied delay, and what we saw was delay did slightly increase in most of the cases, and these are just preliminary results of not no error analysis. But what the point here is that you might have different characteristics and you might not be available to tune all of them together. What we also tried was move on to a different operating system. We were working with Ubuntu earlier, then we moved to FreeBSD. And with FreeBSD, after tuning also, we could not bring down the losses to zero in case of small packets. So these are some of the cases where tuning is not actually solution. And this problem that I've talked till now is a problem related to system specification. And this is actually not the exact problem that we are trying to solve with calibration. But I think talking about this will really make us appreciate the bigger problem of requirement of calibration. And when tuning is not a viable solution, we can see this with this other example. This was again another cyber physical systems experiment, but this time it was a federated setup. We had some resources at ISI, some at PNNL, and we were doing a federated experiment. And what these two graphs show here is the round trip time for packets. Because of just the pure network, the data was going over the internet, and the bottom graph shows the round trip time because of network plus the federation infrastructure, the test bed infrastructure that is required to set up a federated experiment. And what we should focus here is on the y-axis, the scale on the y-axis. If you see the first graph, with just the pure network, the delay was at the max 50 milliseconds, and it was always stable mostly. Right? But with the introduction of this testbed infrastructure, the delay went up to 400 milliseconds most of the time, and then at one place, it even went up to about 1200, 1400 milliseconds. So what we see here is that these are some of the testbed imperfections that the experimenter cannot do anything about. These cannot be tuned, and these add noise to the experimental results, and also variable amount of noise. And in such cases, we need a valid calibration methodology to help users correctly interpret their data. Right. So just to summarize, as an experiment, you need to be able to create a valid representative environment. The current high-level view, the current abstraction that we use, hides away a lot of the essential details. We need to figure out a way to define system constraints correctly, and then to use them to tune our systems. When tuning is not a viable solution, we need to calibrate our results. And with all of these, what we are trying to achieve is a high-level goal of reproducibility. to be able to do repeated runs of the same experiment and reproduce the same result again and again. Now our work has some limitations, and I agree with all of the reviewer comments that we talked about it with. It's a work in progress, and we submitted it as that. These are just preliminary results. We've not done any error analysis. We need to work on it. And as we said, statistics might have gone wrong here. We might not have it correctly. But the point is that these statistics, whatever the experiments that we did, helped us realize the problems within our current setup. But those problems, now that we think of it, are just facts that probably we are not paying enough attention to, and we do not need these experiments to prove them. So, and we also do not have a concrete calibration methodology right now. And this is what we want to be working towards. So looking beyond, the main aim of our work is to figure out how to calibrate results, but these are some of the intermediate problems that we have come up with, and we need to solve them too, to come up to this calibration problem. How do you define low-level system constraints? Most of the tests that do not have a way to do that right now. How do you use those system constraints while allocating the resources? How do you use them to tune systems, right? And then finally calibration. And that is it. Thank you.
Thank you. So first I want to congratulate you for finding and discovering this issue and disclosing it, because it's important for the community to even know that this is an issue that could skew their results. One of the things that I've been known to say is that the worst thing you want is for your test apparatus to be a variable in your experiment. And so being able to finally control that and make sure that it's not interjecting into your experimental results is really important. So I wanted to just quickly go over a very high-level review of the reviewer comments, and then I have some questions to stimulate discussion. First, one of the reviewers said that the work is relevant and if properly structured would represent a useful incremental advancement, and I agree with that. There were two main areas that I thought that the reviewers focused on. One is communicating effectively what it is that you're trying to do. And I don't want to dwell a lot on that, but I thought it is important to point out that the reviews were at the complete diametric opposite of the scale on this one. And so in one case, someone said, it's very clear what they're doing. And the other case, the person said, there's no clear statement of the problem being solved. Maybe it's a difference in, one of the reviewers said that they had very little experience in this area, and the other one maybe did, and so making sure that you communicate effectively for people who maybe are experimenters but don't build test beds.
Right.
Okay. Also, there was one person who said there was a sound method and conclusion, and another person said no actual methodology was provided. So again, what do you do with that, right? The one I really want to focus on, however, is the assurance in the conclusions. So this was pointed out two different reviewers. There were three reviewers. One pointed out that this was the biggest weakness in what you submitted, that there were a lot of implicit assumptions. And what we need to do is find a way to pull those out and make those explicit. And then the next thing is, how do you prove those things? Right, so they said the proposed calibration method is asserted to be accurate and effective, and therefore improves the quality of an experiment, but this is actually not proven. So that leads to my set of questions for discussion, and that is, first of all, what are some of the experimental approaches that could be taken that could provide that assurance so that we understand and can verify that the tool is effective in improving the scientific quality of experiments. And then if we can prove this solution, what can we actually say about the reliability of the test bed? So one of the reviewers pointed out that, well, the network packet loss is only one of the many things that need to be calibrated. What else needs to be calibrated, and how do you know when your entire test bed is fully calibrated and reliable? And then the final thing that I would suggest is what would be good next steps for Pratik and his team? What are some of the hypotheses that they might want to pursue? And with that, I'll open it for questions.
So can I make a comment? For sure. So I think we did not set up the aim correctly in the paper. What we have done till now is to come up with the need for a calibration methodology, and we have just some preliminary results, preliminary ways of calibrating specific cases. And I think in the aim that the longer term aim is to be able to have this solid calibration methodology. And I think in the paper, the way we probably wrote the aim, or the way it came up, was that we already have a calibration methodology, and that is what probably the reviewers were expecting out of the paper, which is not there. So, yeah, which is why they said it's not, there are no experiments to prove that it works.
So, questions? Suggestions?
So this is not a technical question about the work you described, but rather more of a meta question in response to what you just now said. If you were not offering up a solution, what did you envision this paper to actually be? What would it have communicated to the broader community? Let's just say if you submitted it to privacy and security or some other place like that, what would have been your expectation for the reader?
So the expectation is that the way and the experimenters who got, see, the first thing is, for us, people who worked on this thing, we are computer engineers who've been working with network test beds for a significant amount of time. And it took us a significant amount of time and effort to figure out what's going wrong in our experiments. And now, today we expect people from diverse domains to come and use test beds to do cybersecurity experimentation, test critical infrastructure like the power systems and stuff. And for them, they expect the test beds to be this perfect tool which would give them the results, the correct results at time. But that is not true. To make the experimenters realize that you need to pay attention to details while you describe your experiment. You need to be aware that the results that you're getting out of these tests are probably have some noise and error because of the testbed resources. And then to say that there is a need for a calibration methodology to put it out to this community of testbed developers, and that we need to solve that. And it's a hard problem to solve. And we are just starting to attack one piece of it, looking at specific problems. One of the specific things we looked at was network, right? And
I got it, yeah, I got it. So essentially it was a paper that was issuing a warning to the community of testbed users? Would you characterize it that way?
yeah, and then the need...
A warning that says, I know you guys have been trusting this stuff, but maybe that's not such a good idea.
Exactly, and
okay.
And then to understand...
Let me just follow up. Now I'm just going to ask a question out of pure personal curiosity.
Mm-hmm.
So you said that your group, or I took it that your group has been working with these test beds for quite a long time.
Mm-hmm.
And I wonder, I don't know, let's just say that's 5 years. I don't know how long that is. How long did it take you to realize that these things are not reliable?
So Steve, we've been adding these newer and newer capabilities, and we normally, so this is, my wearing two hats here, right? One of the experimenter and then of a testbed developer, like two views of seeing.
I'm sorry to interrupt. I was looking for a number, like 1 year, 2 years, 3 years.
No, we always realize that there are problems with the testbed.
I'm not looking for a rationale for why it took you a long time to figure this out. I'm just wondering how long it took.
No, I think we always, at the back of the mind, we always know that it's not a perfect tool, but yeah.
So I just want to make a point here, following up with Roy, because I think this is kind of important, and that is to understand, how long has this problem persisted, and what experiments have been run on this infrastructure that may have been affected by this, And have we notified those researchers so that they understand that their experiments they ran on this infrastructure may have been affected and they might need to rerun their experiments?
And there might have been some repeatability issues on day one.
Right. Yes.
So this kind of dovetails off that theme in that I think one slide showed 9 hardware variations in your table.
Mhm.
Did you go back at any time and confirm on a particular test or try to reuse the same hardware, identical hardware for a follow-on test to see if there were any variations in that specific, or was it simply 9 pieces of hardware differentiations, or could you go back and confirm, run a second test on hardware 1 and see if there are any variations from using the same hardware?
Right, that's what we show with the second test. We even talk about hardware here. So these are some of the test bed specific properties. Does not have anything to do what resources are allocated to you as part of your experiment. You might have the same hardware multiple times, and what you see is there's variability because of just the pure test bed infrastructure. And then there should be some test bed specific tools that allow users to see that and to help them calibrate the results.
So all models are wrong, some are useful, right? And so repeatability is important, although if it's repeatably not like the real world, that's not so useful, right? And so there's sort of 2 issues here. It seems like, firstly, you can reproduce the results if the system would return to you the specifications of exactly the resources it allocated to you so that you can demand those resources the next time, right? So that's an easy solution to repeatability, although it'd be interesting to repeat it. I think that was the last question, to repeat it with the exact same resources. So that solves that problem. But then there's the problem of maybe I need to supply a spectrum of variable behaviors because the real world, in fact, has a spectrum of variable behaviors with respect to packet loss, and that the results that these people had regarding the down service weren't accurate the first time, and trying to reproduce them gives you a reproducibly inaccurate result.
Right. So the first question was, of the system specification problem, and I think, so you said we could use the same system again and try to reproduce it, but the problem with that also today, with the current test bed infrastructure, is that the level at which you describe your experiment topology is not deep enough. So suppose I used whatever topology, whatever description I used, and I put all of that in my paper. If somebody tries to reproduce the same experiment a year from now, the hardware that the first person used might not be available on the test bed. And if you use that abstract description that we're using right now, it's not a correct description. We need to find a solution to describe your experiment topology more clearly.
Well, my suggestion was that you supply the abstract specifications to the experimenter, but what you get returned is a specification of the actual resources in detail that was allocated in response to the abstract specification. Right. And then when you present your results, you're presenting not just your abstract specification, but the actual allocated resources, so you or somebody else can take the allocated resource set. Right? Whether or not it's available, that's a whole other question. But the repeatability at least would be there if you know precisely the spec returned by the system in response to the abstract spec.
Right.
So just an observation. I've run lots of experiments in Amazon Web Services, AWS, which is arguably not a research environment to begin with. But I've never noticed any discernible differences in my experiments that I think I would have noticed. The things that I couldn't explain, right? So my experiments repeated themselves as I expected, even over long periods of time, like a year or 2 years later. So I just wonder what that says about scale or statistics or anything else.
Right. It depends on what are the kind of experiments you're trying to do. If it's simple enough that the changes in the environment are not affecting your experiment, you would see the same results and you would be able to reproduce. But there are cases where these changes in the environment do affect the experiments, and that's the area we're trying
So
to.
that's another good thing for people to know, right, is when does it matter?
Right. And which is, when if you define your experiment correctly, what applies to your experiment, then yeah, that's what you look at.
So it seems to me that maybe this is what you're describing, but when I hear about you talk about this problem, what I think of is you have a description that's provided of what, an abstract description of what topology you want. And as a researcher or experimenter, you are expecting that to be faithfully honored by the system. That is, if I ask for a 1 Gbps link with, a certain, and I expect the machines on both ends to be able to handle links of that flow, and I expect that latency between those links when it's not flooded to be of a certain value, right? Maybe the max, the tolerance here is maybe between 30 to 50 milliseconds of ping is what I want to simulate. And so when I see a graph like what you have up here on the screen, where you have 1400 millisecond ping, or round trip time, right? So what that says to me is I specified something as an experimenter, and I was given something that I totally did not expect. Right? So maybe that's what your intent is to describe, but to me it might be more meaningful to say the problem is that we're specifying something and the system isn't actually giving us what we're specifying.
Exactly. That's the first part of the problem. But the second part is that you can describe something. So these testbed resources have their own limitations, right? They can only give you so much, and it's not the real environment. So you are trying to emulate, and you can only emulate to make it as real as these testbeds provide you. But what could also help is that whatever inefficiency, whatever error noise is coming into your results because of the testbed infrastructure, if the testbeds could provide some tools to help the experimenters take out that noise, it would help to do better experiments.
Other comments? So the calibration tool that you were proposing was looking at, finding a way to deal with the packet loss. I'm wondering if someone were trying to form an experiment to prove that this calibration improved the quality of another experiment, how would you go about doing that?
I don't have the answer to your question.
And then come to this silence.
Nobody.
You might have mentioned this and I missed it, but in other similar testbed environments, either studying networks or virtual machines to do tests that involve performance or loss like this, are there other examples that parallel the experience that you had, and how did they, if so, how did they resolve that?
I think the problem here is that a lot of experimenters don't realize that there is a problem, and they just, and that's the basis of this thing. They assume that the results that they're getting out of the testbed has no error, there's no noise. It's the exact results, and that is what they assume. They put their results on.
So, I mean, there are others besides you. So
Yeah.
you're really totally ignoring it, or have you shared with them your experience, and are you discussing how they might address it?
So which is what the purpose of this study was, to bring about this knowledge and share it within the community, that you need to be looking at these particular things to correctly interpret your data.
In a test project that I was involved in some time back, and I think Tiff is well aware of this, we had a number of interesting things with a completely physical test bed that was not terribly reconfigurable. Things like exploits that had been designed would sometimes work and sometimes not work. And this was for no discernible reason except that possibly the state of the particular machine where things were in memory at the time the exploit was launched and so on, which, given the foibles of modern operating systems, is not predictable and not reproducible, tended to make things quite different. So there is definitely, no matter how you're doing this, I think there are limits to the degree of fidelity and reproducibility that you can expect, because there are things that you cannot control. When certain interrupts came in from the network may govern where things are in memory at any particular time, depending on what the interrupt caused to happen. And it may be that things are sensitive. I mean, most of the security exploits that we run work by violating the assumptions about clean memory behavior and things like that. And so they go outside of the box, and their results are inherently unpredictable without microscopic level knowledge of exactly where things are and exactly what the values of variables are at that time. So a lot of this stuff is just going to be a fact of life. You'd like to get reproducibility. You'd like to get things that are not far from what you expect. So, you know, if I can ping a machine on the West Coast from my Internet 2 connected machine and CMU and get a 100 millisecond response, I don't think your system should give me a 1400 millisecond response on what seems to be the same kind of link. But there are things that you want to either note that there are artifacts of the way Deter is configured that are going to cause these problems, and they are going to be known unrealisms or something like that. But beyond that, I'm not sure that you can ever completely calibrate something like that without knowledge that, short of being omnipotent, you can have.
So the aim here is to be able to correctly emulate whatever you're trying to test, your test environment. In your test environment, whatever the real world system, it might have variability by itself, and we are not saying that that's wrong, but the point here is that if the system that you're trying to emulate does not have a certain kind of variability, and when you come to a test that you emulate that system, and your assumption is that you have correctly emulated it because you have specified, you have looked into whatever system constraints are applicable to your experiment, you would expect out of the test bed resources that would not be variable in those respects. But what we are showing here is that testbed resources can have variability, and you should be aware. Awareness is one of the things that could help users.
I just have another question. You said something that made me think that most of your users, I guess, hadn't really considered that there might be some intrinsic error in some of these test beds. Do I get that about right?
Right.
Okay. So, do you have any idea what in the world could have led these users to think that? I mean, I personally would never have thought that there was no intrinsic error in a measuring instrument. So I'm just curious if you have some idea of what led your users to think that there wasn't going to be any error.
I know,
You don't know.
no, I don't know what made them think that there's no error in here, but whatever that the reason was, the purpose of this work is to make sure that they don't make the same assumption again.
Yeah, and that's an important thing.
And at least to postulate on that, it could be, and I've noticed this at least in some time in benchmark measuring in some papers, people assume, oh, it's a computer. It can't have errors, it's digital, it's just going to be exact every time, even though we know that that is not necessarily the case.
I just want to say, I think there's plenty of things we could come up with that would explain possible errors, right? You could say, I know that networks drop packets, right? That's a feature of networks. They are not perfect. Or I know this virtualization platform is used by other people. So that's a potential source of error. I think we can probably enumerate a dozen things that you should at least keep in your head about this one might be causing error, this one might be causing error.
Well, I think you are absolutely right. But what I understood was that the users of these test beds hadn't considered those kinds of things.
I don't know that we can jump to that conclusion, but we can at least say,
Well, we don't know, and he doesn't know. We
Yeah.
can't
We're
speculate.
making an
everything.
assumption. We're making an assumption that they don't know, because they certainly, when they had published their results and said they used the deter test bed, they didn't disclose that there could be these issues. So
that's all we can say.
That's all we can say. One of the other things that I'm curious about is, so this is something that you got internal to the ISI facility, right? So what happens when you start federating?
Also, so federation, the second experiment was a federated setup,
Okay,
right?
all right. So
And some of the errors are at the federation level.
Okay.
And then some of the errors are at the virtualization level. So the aim, what we are trying to achieve at the end of it is that for an experimenter, if he defines a system, either our testbed could say that, oh, we cannot give you that kind of environment, it's just not possible. But if the system returns back with a experiment and says I can do it, then it should correctly emulate whatever the user had asked for.
Sure, but in the point of federation, I mean, when you're inside your facility, you control the entire network. But when you federate, you're going across the internet, and you're
Right.
reliant on that entire internet backbone, which could have all kinds of weird issues that could introduce error. Correct?
Exactly. And if he could, I mean, I don't know if all of these are solvable, but if he could, we'll want to figure out what those are and put it out to the user to help them understand their results.
Is there any way to instrument and measure that so that that can be collected along with the other experimental results, so that when something weird happens, the user can go back and look at that and say, hey, this is why I got this weird result.
Right, that's what the purpose is. So in the second thing, if we had these results, right, that something weird happened at a particular time where the delay went up, and we want these results to be out with the experimenter's results, so that or have tools that can read out of this and calibrate the user's results.
That's kind of what Sammy was suggesting. There'd be some kind of spec of how you experiment.
Well, I think what Sandy was suggesting, or maybe I'm confusing people, was that when you request a certain set of resources, you're giving an abstract, but which specific machines did it give you back? So you know the processor, the capabilities of the machines. But now we're talking about as your experiment is running, did something happen on the internet backbone if you're federated, so that you can then go back and include that in your data analysis?
And then just to explain on Sammy's point, he said the first time an experimenter did whatever experiment, and if the testbed could give it back the actual resource description of what it got. The second part would be when somebody tries to reproduce it, it would help if you could take that description and give it to the testbed and get the same kind of resources, which is also missing today.
Exactly. Other comments?
This is a work in progress session, right? And this was the first time I was presenting anything at a conference or a workshop. So I know if you have comments related to that, that would also help if this is appropriate.
Is this your first time?
Yes, it is.
Very good.
I wouldn't have thought that.
Yeah, very good.
So any comments on that would